And sharing screen, that's the step that I forgot last time. So now we're recording. Now this is our official start of data mining, and everything we say, the NSA can hear us. Okay, and whoops. Last time, the Git repo, I'm doing the Git repo a little bit different than I've done in classes before, so I kind of messed things up on accident. In this future folder, there was supposed to be sort of the outline of the other topics that we're going to discuss in this class, and it wasn't there last time because I messed up my Git commands, but now they're here. And so just as a high-level thing, there's 11, starting counting at 0, different topics that we're going to be covering. Most of them like 1 week's worth, some of them 2 weeks worth of material. And the first exam that we're going to have is going to cover this linear algebra notes that we passed out last time. We'll cover the rest of those notes today. And then we'll start talking about this PageRank algorithm today, not today, next week and the week after. And that'll be the material for the first exam. The sort of common theme between all this material is just that it only involves computation, no like statistical reasoning at all. And then after that, we'll move into the learning from data textbook. Again, the common theme of the material at the beginning, those first two computation things, is they're required to understand the stuff in the textbook that also incorporates statistics. So we'll talk about the stuff in the textbook. That's these 4 or 5 topics here, and then talking specifically about text stuff and applications, which gets into more like researchy level things, and that'll be the last midterm. So this is the second midterms, all the stuff from the textbook, third midterm stuff from the researchy stuff. Today in class, we'll be going over those notes, the computational linear algebra. We sort of started that with the first few problems and the big O notation, big omega, big theta, and seeing that it's things can get a little bit different when you talking not just about runtimes, but about well, if you have multiple variables, or when we will see eventually talking about things like statistics instead of just runtimes, and we'll have things where there's fractions and other weird formulas that don't show up in runtimes. That is exciting. Okay, so yeah, we'll do a warm-up problem here with some of these problems before getting into the rest of the notes. Before we do the warm-up problem, any questions about anything? Okay, so let's look at problem number 2. And I should have numbered these things going down, but this one right here was where we're going to start. The a over b equals a over b squared. Let me zoom in a little bit. There we go. And if there's ever any time where you can't see what's on the screen, need it zoomed in, zoomed out, whatever, just let me know and I'll fix things. We're going to do this ab equals a over b squared thing. And so the general procedure, you have the thing on the left is f, so f divided by g. The thing on the right, a over b divided by a over b squared. Simplify that and you get b, take the limit as all the variables go to infinity. And what is that going to approach? Somebody shout it out. That'll go to infinity. And so what do I put over here? Okay, so we'll go back to our definition right here. Is infinity less than infinity? No, it's not. Is it greater than 0? Yeah, so let's put the omega. Any questions about that problem right there? Okay, the next one, we'll do the one right below it. Here, our f over g will be a over b divided by a squared over b squared. And that's going to give us b divided by a. The limit here is a little bit more, I don't know, subtle. So let's head over to Wolfram Alpha. Again, this is not a calculus class. You don't have to compute anything by hand. We have computers. We should take advantage of them. So wolframalpha.com, let's do limit. Well, I'll start by typing in the wrong thing, and then I will type in the right thing. Limit as b goes to infinity of the limit as a goes to infinity of b divided by a. Is that the right thing from the problem there? So b divided by a, yep, that's right. And here, if I type it in this way, then I'm going to get the answer is 0. Actually, though, the answer is not supposed to be 0. Here, what I typed in is doing the limit first of a, and then after doing that, do the limit with respect to b. Let's make this bigger. So we want to be careful to make sure we're doing both of the limits at the same time. And in Wolfram Alpha, a way to do that is to put a comma between the things that you want to take the limits of. Do that, and it's going to tell us the limit does not exist. So the right answer for this one right here, it's not O, it's not omega, it's not theta, it's just totally uncomparable in an asymptotic sense. Yeah, so I guess the main trick thing here is just if you are using Wolfram Alpha or using something to compute the limit for you, make sure you're doing it correctly. Any questions about either of those problems? Hannah, right?
Yes. The reason behind that is because they could be approaching infinity at different rates.
Yeah, we could go to infinity a first or go b first to infinity, or we could go sort of at the same time to infinity. So yeah, the little bit getting philosophical, why doesn't the limit exist? Yeah, that's the intuition. They could be going at different rates. Good question. Any other questions? Okay. So the real point of us talking about this big O notation is so that at various points in this class, we're going to have lots of complicated formulas. And we want to be able to talk about not the complicated version of those formulas, but a simple version of those formulas. Only talk about the actual terms that we care about that are going to affect things. And so you're probably used to that from data structures class. You might often have runtimes that look something like this first problem right here. I'm on problem 3 right now. This is just the next page over. And the intuition that you probably developed is that when terms are smaller than other terms, so like this term right here, an n squared log n. Oops, what did you do? This term right here, smaller than this term right here. And so this n cubed is going to dominate. And so we can just sort of get rid of that because it's not actually going to affect things. Similarly, the log n is smaller. And so you can just get rid of it. And you keep the O of n cubed as the final results. In this class, some of the formulas that we'll see, it's going to be, so it's 100% okay if you can do it all in your head and simplify things in your head that way. But I'm going to do this same problem just a little bit more carefully so that when we get to more complicated things like number 2 down here, we'll have a little bit more step-by-step approach on how to do the simplification. And so when I said that this right here, this term right here was smaller than the n cubed, anytime you think smaller, you should think omega, omega smaller. And so formally, I could say that n cubed is omega of this other term, 5n squared log n. And because this term right here is inside the omega of the n cubed equals omega of this term right here, that's why I can get rid of it. And so in order to know if I can get rid of a term, I have to check, is this term right here omega related as omega to something else? Or in other words, is n cubed equal to omega of this term? If it is, I can get rid of it. So down here, we'll start with the ab squared. Is ab squared omega of 3a squared b? I don't know, that one's maybe a little bit tricky. We'll save that one for later. Is it omega of AB? I don't know. Let's go to the simplest one possible of the 10b over here. Start simple. So we want to know, is this, we're going to compare this term right here to this term right here. And so our F will be the AB squared, and our G will be the 10b. And doing the division, F divided by G, just add a little division sign right there. Then actually working it out, we'll get that's equal to AB over 10. And we'll do the, take a limit as A and B go to infinity. What do we get? The limit as A and B goes to infinity of A times B divided by 10. Infinity. And so go back up to our definitions, we'd see that that is in fact an omega relationship, that F equals omega of G. And so I'll write that out, AB squared equals omega of 10b. And because of that, this 10b term is not going to influence anything in the limit, and we can just get rid of it. If we repeat that same procedure for the AB, then switch colors, add a little dividing line. So now our F over G, AB squared divided by AB, that's going to be equal to B. What's the limit of B going to infinity? Also infinity, yes. So we're also in that same omega case. So AB squared equals omega AB. And so this is also, again, omega is like less than. So AB is also less than AB squared, so we can get rid of it. And now we're just to the two more complicated terms right here, AB squared and the 3A squared B. Switch that color again. And do the division, AB squared divided by 3A squared B. What's that equal to? B over 3A. What's the limit? Yeah, it doesn't exist. All right, D and E for not exist. So there's no like omega theta relationship between these two terms right here. So we can't cross them out. We can get rid of that constant factor up front though, and just say that this is equal to O of AB squared plus A squared B. Any questions about that particular problem? Okay, then don't follow along with me. I'm going to jump to the very last page of the notes just so you can see where we're going, and then we'll come back up here. So jumping to the last page, where are we going? So our goal is we're going to have sort of mathematical equations like this. An equation like this will be, I don't know, maybe it looks complicated to you right now, but by the end of the semester, this will look like a simple trivial equation to you. We'll see things like this so often. And our goal is just to be able to look at it and tell what is the runtime of this equation going to be in terms of the size. So A here is a matrix. These X's are vectors. And so in terms of the size of these vectors and these matrices, what is our runtime going to be? So that's what we're building up to. That's why we needed these sort of initial asymptotic notation tools. And what we're going to do next is we're going to see a lot of individual isolated cases of individual operations. What are their runtimes? And then we'll put it all together to be able to compute those formulas like we saw at the end of the notes. Alex?
Do we need to keep a 3 coefficient in there or no?
Question is, do you need to keep this 3 coefficient here? And the answer is no. Any constant factors you can take out. Maybe I'll also say on the first midterm exam, you're not going to have I'm not going to necessarily ask you, like, given this formula, what is the simplified version of this formula? Instead, what the sort of problem is going to look like is the problems at the end here that's given this formula, what is the runtime for computing this formula? And so as intermediate steps of doing that, you'll have to be able to simplify things. Good question. Any other questions so far? Okay, so the section 4 of the notes here is talking about, so BLAS and LAPACK. BLAS stands for the Basic Linear Algebra Subprogram. LAPACK is the Linear Algebra Package. These are two sort of frameworks for doing computation. I pronounce this LAPACK because I'm from LA. Everybody else in the world pronounces it LAPACK. So you can tell where people are from based on how they pronounce it. Pretty much everybody in California, West Coast people pronounce it LAPACK. Everybody else in the world, sorry, California and West Coast people pronounce it LAPACK. East Coast people outside of the US pronounce it LAPACK. But BLAS is BLAS to everybody. And these are systems that are used behind the scenes in Python. You don't have to interact with it directly at all, but you will have to know the properties of these systems in order to know how your Python code is, how fast it is or how slow it is, how to make it faster. So sort of talked last time about the idea of sparsity. Sparsity is just counting up the number of non-zero entries in a matrix. So here, the sparsity of this in Z is the notation of A, just equal to 2. And we're going to be writing our runtimes of our various operations in terms of the sparsity of the matrix. So that's how it's going to come up. Any questions about any of this stuff at a high level before we get into the actual operators and their runtimes? Okay. We're going to skip here problems 5 and 6 and jump on to this section 4.4. So BLAS is divided up into 3 separate sort of levels. The first level being operations that only are related to vectors. So in this case, problem 1 here, we have a vector scalar multiplication. So it's a BLAS level 1 operation. And the goal of these problems is just to be able to identify what is the runtime of an operation like this when you see it. This dot right here is just to emphasize that there is an operation going on, but this is also written equivalently as 5x, no difference. For all of these problems, there'll be 2 cases, a dense case and a sparse case. So the dense case meaning that the vector is just represented as a dense vector. We're storing all the values. The sparse case, we're only storing the non-zero values. And for all of the operations, the runtimes are going to be exactly the same. Theta of in for the dense case, and for the sparse case, it's theta of in Z of X, the number of non-zero values of X. That if you have non-zero values everywhere, then you have to multiply them all by 5. If you have only one non-zero value, you only have to multiply that by 5, and everything else can stay the same. Here, so I'm going to be very careful today with all of my thetas and O's and omegas. And so this is an intentional theta right here. It means that it is both an upper bound and a lower bound. There will be some times where I'll be writing O's and it is only intended to be an upper bound. Any questions? Is this simple so far? Couple head nods. So 0 times x, even if you're multiplying by 0, same thing, you still have to do it. The libraries are not going to be, they're not going to try to be smart and inspect the values to try to skip it and just replace everything with zeros. So the runtimes are the same as above. So write it out. Dense, theta in, sparse, theta, in and z of x. Slightly more complicated, number 3 down here, we have 2 vectors. This is a dot product going on. This T operation right here, the transpose, always happens in constant time. Every library that stores vectors, matrices, higher order tensors, whatever it's storing, if there's a transpose going on, it just has a single bit somewhere where it decides, like a Boolean variable saying, is this transposed or is this not transposed? So it doesn't actually in memory try to do anything. So this is just a dot product operation right here. There's nothing else going on. You can sort of think about it maybe as in like a mathematical sense of multiple operations, but from a computational sense, it's just a single dot product operation. And the runtimes, so dense, still just theta in, sparse. Now we have to look at all the non-zero entries in both of them. So it'll be theta in z of x plus in z of y, like that. Any questions? Yes. So the question is, here we have 0 times x, y is dense theta of n right here. So first of all, when I write dense and sparse, these are the formats that I'm using to store the matrix in. And I'm not going to talk in detail about like exactly what like underneath the hood data structure is being used physically in memory. It's just everything calls it either a dense or a sparse. Every library has a dense version and a sparse version of things, and they always just refer to dense and sparse. And so we just need to know the properties of dense and sparse matrices or vectors. In this case, we're multiplying by a 0, so we could have a special optimized thing if we do a lot of multiplications by 0 for some reason, where we just don't do anything and return a 0 vector automatically. Nobody does that though, because multiplications by 0 are extremely rare and not worth the overhead of doing all those things. So it's still, even though we have a 0 here, we could special case it and do things. We still have to, it's still treated just like an arbitrary constant, and it goes through the same constant multiplication process. Did that answer your question? Yeah.
Is it theta of n on purpose, or is it just theta of n?
So here, these top ones, it's a little bit maybe hard to read. These top ones and dense are in. These bottom ones are the actual name of the variable. In is the dimensionality of the vector. So whenever we use this asymptotic notation, big O notation, whatever is inside of the parentheses has to be a scalar. And so we need a scalar here. In is a scalar. X would not be a scalar. So something like theta of x, this never makes sense to write. Because everything in the asymptotic notation needs to be scalars. Here we do have an x inside of here, but that's because the in z is a function. In z is a function that takes a vector in r to the n and returns a scalar, which is just a number, how many non-zeros there are. So this final result, even though it has a vector inside of it, is still a scalar that's inside of the asymptotic notation. The last one down here is, so this is called the L1 norm of the vector. How many people here have seen the L1 norm of vectors before? Used them a little bit. A couple people, not a whole lot. That's okay. So we're going to skip this problem 4, go into the next page, problem 8 right here. There's a bunch of different, these are called vector norms that we'll be using throughout this class. And so you'll need to know the formulas of them. The 2 norm right here is the most common. It's also known as the Euclidean norm or the Euclidean distance. So we'll do that one first. And this is defined to be the sum from I equals 1 to n of the x sub I squared to the 1/2. So it's just normal Euclidean distance, Euclidean norm that you've definitely seen before, even if not written out maybe so abstractly. These other norms are sort of generalizations of the Euclidean norm here in the L1 norm. we replace all these 2's with absolute values. So it'll be the sum from I equals 1 to n of the absolute value of x sub I, like this. For any of these norms, in order to compute them, we have a single summation right here. So summations, think for loops, looping over a bunch of these scalars. The x sub I is the ith index of that particular vector right here. So computing them is going to take linear time. And it's theta of n because you have to visit all of them, and you will visit all of them at most once. So for dense, theta n, and then the sparse, we don't need to worry about the 0 values because the absolute value of 0 right here is 0, so it'll skip over those, and so it'll be theta of nnz of x again. So anytime, again, the takeaway message, anytime you have one of these blast level 1 operations, which is just anything involving only a single vector or a vector and a scalar or 2 vectors, but no matrices. If it doesn't involve matrices, then these are always what the runtimes are. It's linear for dense, and it's the number of non-zeros for sparse. Any questions about any of that? Yeah. Okay, so the question is number 3 here, we have a slightly different value down here for the sparse than the other ones. And the question is, why is that? Great question. The answer is that here we have 2 vectors in our operation, the x and the y. And so both of those sizes of those vectors need to be represented down here in the runtime, because we have to look at the entries of both of the vectors. All the other operations only involve a single vector, and so that's why they only had a single n and z inside the asymptotic notation. Yeah. And the question is, how does transpose affect sparsity or anything else? And the answer is transpose will never have an effect on runtime. Whenever you call, like, if you've used NumPy before, if you've taken the transpose of something in NumPy, or in MATLAB, if you've taken the transpose of something in MATLAB, it doesn't actually compute the transpose. It doesn't actually do anything. It just has a little Boolean variable somewhere saying, this is now transposed, so that it does the loops, any loops that it has to do in a different order. So there's no computational overhead to transposes. If you're not able to visualize, like, I don't know, maybe algorithms that actually implement any of these particular operators, that's 100% okay. The important thing is just when you see these operators in an equation to know what the runtime is going to be. Great questions. Any other questions so far?
I'm just wondering why theta of n for dot
Question is, why is this going to be theta of n for the dot product in the dense version? We can write some pseudocode here for what the dot product is going to look like. So I'll do it over here. Let's do it in orange. Say dot equals 0 for I. I'll do it in legitimate Python code for I in range n dot plus equals x I y I, like that. And so we have a single for loop going over the n. It does have to do 2 variables, but it doesn't both at the same time. It's not 2 nested for loops. So that's where you get the linear from.
Oh.
Okay, things will get a little bit, well, they say everything's essentially the same here for this level 1. Things get a little bit more complicated in the level 2 and the level 3. Level 2 is specifically for matrix vector operations. And so that looks like AX or X times A. And we're not going to talk about those specifically because it turns out to be exactly the same as if you treat this X right here as a matrix and that just has one column or one row in it. And so we're only going to talk about the BLAST level 3, which is for matrix-matrix operations. And a vector, again, is just a one-dimensional matrix. So this will totally subsume the discussion of BLAST level 2. There's a number of subtleties in the runtimes here. But the main thing to take away is that anytime you have two matrices, A and B multiplied together, these are the dimensions up here. So M by N and N by O, the inner dimensions match, the N and the N match. It's required to have well-defined matrix multiplication. Then the runtime is going to be O of M and O. So just each of the dimensions here get multiplied together. The n's required to be the same. So that's how I remember it, that it doesn't get included twice because it's required to be the same. So one each for all the unique dimensions. And it's very important here that you remember this is a big O and not a theta. We actually don't know what the optimal runtime is for computing matrix multiplication right now. That the best known algorithm takes time O of n to the 2.373 right here. And this is a super complicated algorithm. I don't know anybody who has actually read the paper and understands like how this algorithm works. I don't think it's ever actually been implemented before. Certainly no BLAST library actually implements it. It just has too expensive of a runtime constant overhead, so nobody uses it. You need like matrices on the order of billions of billions, like billion raised to the billion power, rows and columns for the constant factor to stop being important. So in practice, people use Strasson's algorithm or a variation of it, which has this runtime right here, into the log base 2 of 7. So that's a little bit better than the sort of cubic runtime that we have up here, but it's close enough that everybody just talks about matrix multiplication as being cubic. Actually, the best, we know that matrix multiplication cannot be faster than n squared log n. This is a lower bound on the runtime for matrix multiplication, but we don't know where between this runtime and this runtime that it actually sits in. For the purposes of analyzing runtimes of algorithms, it's good to know all of these other things, but this is the formula that you'll always use whenever you see matrix multiplication. Use this formula right here. Any questions about that? Okay, if you are curious in those sorts of things, like how can we not even know how fast to compute something in, Wikipedia has a great article. For sparse matrices, the key formula is this one right here. In PyTorch and in every library that I know of, you can only multiply a sparse times a dense matrix. You cannot multiply two sparse matrices together. You can only do sparse times dense. So if we assume that A here is sparse, so n and z of A right here, the number of non-zeros, and then B is dense, n times O, the dimensions of B right here, n times O. So it's the number of non-zeros of A times the dimensions of B is the runtime. Okay, that's maybe a little bit abstract. Well, if we get to the some of the formulas, that'll start making things click a little bit more. So scrolling down, going to the next page over here. Problem 9 here has all of these or some examples just in isolation. Here, this is addition, matrix addition. We didn't explicitly cover matrix addition, but this is exactly the same. You can think of matrices as just a vector with extra structure. So this is the same as vectors. And so for dense, here in this case, the dimensions have to match. So the dimensions of A and B both are going to be, I'll say n times m. Whenever I use this colon notation, the thing to the left is going to be a variable. The thing to the right is going to be the dimensions of that variable. So it's an n times m matrix. Other professors you might have seen sometimes write out something like r to the n times m means the same thing. But computer scientists are lazy. You don't want to write that r when we don't have to. So dense, you just have to visit every entry once and exactly once. So that'll be theta of nm. If you treat these as vectors, there are nm entries in the vector. The size of the vector is nm, so that's why it is theta nm. And if they're both sparse, in this case, both of them can be sparse. Both dense. Then it'll be just like we had before, the theta n z of a plus n z of b. For the multiplication, this is just basically copying out what I had in that paragraph above. If they're both dense, then go with the O notation, O of m in O. Here, A will be m by n, and B will be n by O. And so this is exactly what I wrote out before. Again, it's important that you put an O here. I've written theta everywhere else because it is in fact theta. It's both an upper bound and a lower bound. Here, I'm putting just an O, not a theta, because this is only an upper bound. And we actually don't even have an algorithm where it can be a theta. If the left-hand side, if the A is sparse, A sparse, B dense, then just copying again from the paragraph n and z of A times n times O. Any questions about those runtimes? Okay. So here we'll do number 3. I'll leave number 4 as an exercise. Here, x here is a vector, not a matrix. So I can say something like A will be m by n, and then x, what size should x be here? Should it be m or n? N, yes, because it's being multiplied on the right, has to match the thing on the right. So in the dense case, here, so okay, we have just an n. I could also write this as n by 1, and now that's sort of interpreting this as a matrix, and now we can use the same formulas that we had before. Just the O value is equal to 1. So now it'll be O of mn like that. And then in the sparse case, which of these two variables is allowed to be sparse, A or X? Yeah, just the thing on the left, A. So A sparse, X dense. Then we have O of n and z of the thing on the left times the product of all the things on the right. So just n, like that. So yeah, anytime you see vector matrix, that's just a special case of matrix. And so the only thing that I actually remember is the matrix case and figure it out from there. Any questions? Okay, these are all, I promise things will get more interesting in a little bit. Before we get more interesting though, we have to do a couple more cases. Let's see. Actually, this is an interesting problem right here, but I'm going to leave that one for you all to work on, problem 10. And we'll come down. Matrix chain ordering problem. Okay, here we go. This is starting to get into the interesting stuff. So if we have multiple matrices, so in this case, I just have 3 as an example. It turns out that matrix multiplication is associative, so it doesn't matter how you put the parentheses. It doesn't matter the order that you do the multiplication in from a value perspective, from like a pure abstract perspective. But from a computational perspective, it does actually matter. And actually determining the optimal ordering of matrices is a relatively hard problem when there's a lot of them. And when you're programming on your programming assignments in this class, you'll have to be careful about your order of matrix multiplications, because there are some orders that will be catastrophically slow and will take years and years to finish, and others will be very fast and take seconds to finish. So here, what is the runtime of AB times C? Well, AB is, first let's write, what is the shape of AB, A times B? AB, the shape of it. Yeah, M0, the middle ones go away, the N go away, so MO, and then the runtime will have O of MNO. Now we do AB times C. I'll say this is Z1 equals to AB, so that I can just write Z1 times C down here. And that way there's always on each line just going to be a single operation going on. Z1 times C. Well, Z1 has this shape, M times O. C has O times P. So that's shapes check out. We can do this operation. And we'll get M times P as our final shape. And the runtime O of MOP. This M times this O times this P up here. MOP. Our total runtime is going to be the sum of these runtimes right here. And in this case, there's not going to be anything that we can cancel out. These two are uncomparable with each other because they just use different variables. There's no P up here. There's no N down here. And so we'll have to add them together. Can't simplify. MNO plus MOP, like that. For the next problem, what if we reparenthesized in a different way? Well, we'd have Z1 equals now B times C. The shape of that, what's the shape of B times C? NP. What's the runtime? NOP. NOP. And then the next line we'll do A times Z1. So A, the shape, M times N, N's match. There we go. So we get the MP, the N's going away. The shape, final shapes, they match. That looks good. Just double checking. We're not making any mistakes here. And then what's the runtime of this operation right here, the A times Z1? So we get the M from the A, the P, sorry, the N from both of them, and then the P. So yeah, M, N, P. And so our total O of NOP plus MINIP. NOP plus MINIP. And so depending on the actual size of these matrices, you might prefer one of these parenthesizations over the others. And in particular, under what conditions would you choose the former parenthesization over the latter? Well, if MNO plus MOP happen to be less than NOP plus MNP. And there's not really any simplification that you can do about this. There's just, you have to keep track of all four of those variables everywhere, and you plug in the numbers, see which one is smaller, and choose that option. Any questions about that? Sorry, simplifying. Oh, okay. Yeah, so the question is, here when I added these two O values together, I got this O value down here. And then I made a comment about simplifying the O value. This goes back to the problems we were doing at the very beginning of class. I think it's problem 3 in the notes, where you have a big O expression and you're crossing out the terms that you don't need, that don't matter. And in this case, you can't do that because both of them matter. But when we get a more complicated formula like this, I don't know, with maybe 10 multiplications or something, there'll be more terms in there and things will start canceling out. So that last problem at the very end that we'll get to will have that cancellation going on. Let's see, that's a little bit on the abstract side. If we come down, let's do problem 15. When you're dealing with vectors is when the order of the multiplications is the absolute most critical. So problem 15 right here, we have 4 vectors being multiplied together. Say that the vector x has shape in by 1, and I'll also write out the x transpose as 1 by n, just so that we can check our matrix multiplications here. And we have a number of possible ways that we might want to do the parenthesization. Maybe the most obvious, the simplest one would be something like just going left to right. Do the x transpose x, do that, then add this x transpose over here like that, followed by another x over here. And if we were to do this, then what we'll see, so let's go through the same steps again. Z1, we'll do the shape, writing out the shape and the runtime. Z1 being x transpose x. And so what's the shape, the final result of x transpose x? So it'll be a scalar because we have the x transpose 1 by n times x in by 1. The n's will go away, we'll get 1 by 1. So the scalar, yeah, 1 by 1. The runtime here, this is back to the blast level 1, the linear runtime. We're just doing everything as dense right now. And so, yeah, let's go ahead and write it as theta, theta of n to compute that right there. Well, let's stick in red. So Z2 equals now Z1 times X transpose. And so our shape here, we just have a scalar multiplied by a vector, so it'll stay as the same shape, 1 by n. The scalar multiplication, also theta of n runtime, scalar multiplication. And then this last one over here, multiplying Z3 equals Z2 times X is going to give us, yep, back to a scalar, thank you, 1 by 1. Also, so it's a dot product, so runtime theta n like that. And if we added all that up together, we could get the total being theta of 3n, but then simplifying that to theta of n. So this is one choice of parenthesization, and it's getting us linear runtime, so that's probably a pretty good choice. Let's switch to blue here, and I'm going to keep going down here on the right-hand side of the page, but it's still this problem right here that I'm working on. Let's consider another choice where I did something like doing the x transpose first, like that, followed by x transpose over here, followed by an x over here. And so our Z1, x transpose, our shape, and our runtime. What's the shape of the x transpose? Yep, n by n. So n by n runtime. It's not a dot product, so we have to go to that blast level 3 formulas, taking the outers, the n's, multiplying the inner once, and so the runtime n squared. And this will be a big O n squared because it's using that blast level 3. So O instead of theta. And already we can see that we're going to get a worse runtime than the previous one because the previous one was linear and this one is quadratic. I'll just go through the remainder of the steps here. Z2 equals Z1, oops, X transpose Z1. Our final shape will be 1 by n. We have a vector times a matrix, so we'll use the level 3, get the n squared again. And then finally with the last one, z2 times x. Here we're going down from a vector down to another scalar, 1 by 1. And this one would be in, it's just a vector operation, so we could do it in linear time. Adding those things together, O of 2n squared plus n, which simplifies to O of n squared. And so depending on, again, the takeaway, depending on how you actually do your parentheses when you're implementing things, you'll get different runtimes. And so it's important to pay attention to doing the parentheses well. Any questions about any of the steps on these problems here? Yeah.
Can you explain why this is always rather than C?
Question is, why in the bottom in the blue did I use big O, and in the top in the red I used the theta? The answer is that in the top I was only using the blast level 1 operations, only vector inner products or scalar multiplications, and those have the theta runtime. So dot product, scalar multiplication, dot product, all theta, strictly linear runtime. Oops, wrong button. In the bottom ones, I was using, it's 2 vectors, but in order to get the result is a matrix. And so I have to use the blast level 3 level operations. And so anytime there's a matrix involved in any way, you have to resort to the O instead of the theta. You can't be totally strict about what the runtime is. Good question. Any other questions? Oh, yeah.
It might be sort of in the same vein as that, but like the last one, because we're multiplying like a 1 by n vector. I mean, I guess it's still by n.
Oh, yeah. So in this last one, I could have, Z2 right here is a vector, X is another vector. And so I could, it is just a dot product. So I could replace this with theta right here. But in order to, because these have no sort of omegas, no lower bounds going with them, when you add them all up, this extra tightness, this extra strictness of saying theta goes away, and you can only make a final statement about big O. You can only say what the upper bound is, because these have no lower bounds. Okay, let's keep going on. Yeah, so the next few problems are just variations on that, looking at different parenthesizations of things. And all of that, again, is related to BLAS. Again, you're not working directly with BLAS in this class, but you will see it appear in various forms and different documentations and things that you'll have to read. And anytime you see BLAS, you should think just matrix operations that are like multiplications. The B is for basic, so it's the most basic things. LAPACK is for things that are a little bit more common. A little bit less common. LAPACK is for things that are less common. The most common of which, the things that you will see the most often, are the inverse and top K eigenvectors. Those are the 2 things that we'll be using. Both of these reduce, or the inverse reduces down to matrix multiplication. That's how it's implemented as various matrix multiplications. So it's still O of n cubed. Here, it's actually n cubed and not an MNO or something like that, because you can only take the inverse of a square matrix. So that's why it's n cubed right here. Although faster algorithms exist again, and we don't know what the optimal inversion algorithm is. And then for top K eigenvectors, so however many eigenvectors you're computing, K, it's n squared times K. So if you're computing all of the eigenvectors, that is also a cubic runtime. So you'll often hear people talking about the runtimes of inverting a matrix, matrix multiplication, and eigenvector computations as like interchangeable things. Any questions about that? Okay, we're almost to the most interesting problems. A little bit more definition things. Matrix norms. So we saw vector norms before. Matrix norms are different, defined differently than vector norms, even though they look exactly the same. It uses the same notation. So you might hope, you might want this to be equal to some sort of Euclidean sum-looking thing. But actually, the Frobenius norm with this F stands for Frobenius. F equals Frobenius. This is the equivalent of the L2 vector norm. It's the Euclidean sum I equals, or sum over the i's and the j's of aij squared to the 1/2. So doing all the just Euclidean distance sort of calculation, that's what the Frobenius norm is. We'll be using that quite a lot in this class. Leave it there for one more second if people need to write it. And I'll write the L2 norm. The L2 itself is just out of the page, but I'll write it right here. The L2 norm is actually equal to the largest eigenvector. Sometimes you'll see that mathematically written out as, okay, I'll look at the formula so I get it actually written correctly for you all. The largest eigenvector, you'll see this written as the max ax2. This norm right here, a times x, vector times matrix, is a matrix. So this is now the vector L2 norm, not the matrix L2 norm, divided by size of x2, where x is not equal to the 0 vector. In this class, we're going to be talking about PageRank next. PageRank involves a lot of eigenvector computations. And so we'll be thinking about eigenvectors quite a bit in this class and seeing the L2 norm come up in that context. Again, if like eigenvectors are not 100% clear to you, recommend the videos linked at the top of this notes to get a refresher. Yes.
So the L2 norm for matrix would be like the Frobenius norm?
Good question. So the question's about shapes and norms. And every norm, no matter whether it's a vector norm or a matrix norm, let's do it in red up here. Every norm outputs a scalar. We know we're using the vector norm. Just when the thing inside of it is a vector. Yeah. Thing inside vector, and it's a matrix norm. When the thing inside is a matrix. And that's the only way to know which one you're actually using. I guess technically here, since I've said eigenvector instead of something like singular values, eigenvectors are going to require square matrices. So we'll pretty much we will only be concerned with square matrices in this class, in the L2 norm of a square matrix. We won't be talking about non-square matrices when we're taking the norms of vectors. Or sorry, we won't be talking about non-square. We won't be, everything that we take, every matrix that we take a norm of will be a square matrix. If something is not square, then it will be a vector. Did that answer your question somewhere, or?
Yeah, I just wasn't sure why, so the
L2 norm would be equal to the largest eigenvector. And then we then.
I see. Sorry. This should be eigenvalue instead of eigenvector. Yeah, thank you. Good catch. Because the output is a scalar, not a vector. So based on these two formulas, we can know what the runtime of computing these matrix norms are. Coming down here, the runtime for computing this matrix norm is going to be O of, it's an eigenvector computation. The runtime of computing eigenvectors is k n squared, where k is the number of eigenvectors or eigenvalues that we're computing. And in this case, k equals 1 because we only need the top, the biggest one. So it implies the final runtime is just quadratic. And then for the Frobenius norm, it's just a sum over every element in the matrix. So the runtime also quadratic. 1 for each element in the matrix. Any questions about anything that we've done so far? Oh, yeah, no. It's Noah, right? Yeah, go ahead.
So the first one, how is it taking the L2 norm A the same as computing the top K?
How is, so the L2 norm of A is defined as being the largest eigenvalue. So, yep. Hanan, did you have a question too?
Yeah, but I just
Down? Okay. So the Frobenius norm, question is, how did we get the runtime of the Frobenius norm? Here, it's a loop sum over ij. So this is a nested sum. We got it. It's too ugly. Sum I equals 1 to n, sum j equals 1 to n, aij squared to the 1/2. This squaring right here takes constant time for each element, but then we have summing two nested loops right here. So that's where the n squared comes from. And then this square root up here, constant time. So n squared overall. So yeah, the k comes from, is only involved in the eigenvalue computations, eigenvector computations. And in this case, we're only doing one, k equals 1. Down in the second one, it's just two nested for loops. You compute it directly. It's quadratic. Okay, so the remainder of the last set of problems here is putting it all together, you have some reasonable expression here and figuring out what is the runtime for it. we have about 10 minutes left in class, so we'll do one of these problems, but just to make sure that we don't get distracted, I want to make sure to talk about that second set of notes that I passed out and what to make sure that you've done for next week. So in that second set of notes, it's on the beginnings of our discussion of PageRank. PageRank is an algorithm. It's basically how Google, all these websites, rank all these search engines, how they rank websites. And we're going to see how that all works. In the notes on the first page, cool video by a guy who's super important at Google. Recommend you watch it. Not very technical though. The actual reference that we're going to be using for PageRank is this research article right here. And it is you can download it on the website. If you just click on the PageRank link, Then it's this deeper inside PageRank.pdf. It's like 50 pages, so I didn't print it out. There's only, a lot of them are going to more technical detail than we'll need. There's only like, I don't know, maybe 10 pages of technical detail that we'll need. And there it is. These sections right here are what I would like you to try to read, do your best to understand before class on Wednesday. In particular, in this set of notes, I'm not really going to go over the definitions of various terms in class. I'll do some high-level stuff, but my expectation is that you've completed problem 1 and 2 in these notes, just defining all the various terms, figuring out where they are in there, and so that when we come into class on Wednesday, we can get right into like actually understanding why we care about these terms, rather than just going through copying over the boring technical definition. I mentioned before about the quizzes for definitions that you'll have to have memorized. This problem 2 is going to be exactly what your first quiz is going to be. That I will just it will literally be exactly the same sheet of paper. There are 8 definitions that I'm expecting you to know what they are, and for your quiz, you'll come in and just write out those 8 definitions. So the quiz will not be on Wednesday, but it's good to just start practicing that to get those definitions in your brain. Any questions about what to do for next Wednesday? Would,
Because I feel like the speech I told you.
So yeah, so inside here on problem 2, there's a couple of actual terms, and then there's a couple of just like random letters like this. And you will have to, these random letters have definitions inside of the PDF file that you're supposed to read. That it's not just a random letter. This P bar thing right here has a 1-sentence definition inside the document that you're supposed to copy over. Good question. Any other questions about what to do for Wednesday? Okay, then we'll jump back over to the problems for the first set of notes, the linear algebra notes, and we will work out the runtime for one of these problems. And actually, there is one typo that I accidentally printed out a slightly too early version. Number 3 down here, this is what it's supposed to look like. I think yours has an extra summation inside of the 2 vertical brackets. So it'll be the same whether it's the L2 or the F. Sure, yeah, go ahead and change it to the Frobenius. Okay, so the main tricky part about these problems, well, there's a number of operations that are going on here. We have a matrix multiplication, we have a matrix inversion, another matrix multiplication, and then a matrix vector operation. And we have to figure out what is the right order, what is the optimal order to do all of these computations in. In general, when you're like figuring this out by hand, there's not really anything better than just trying all the combinations and seeing what ends up being the best. Working through these 4 examples here, I think you'll see there's some patterns that start to emerge about heuristics that you can use, but there's not any like definitive set of guidelines. General heuristics are anytime that you reduce the shape of the result, that's good. Anytime you make the shape bigger, that's bad. So make shape smaller is good. Make shape bigger is bad. And on these problems here, if you just use sort of a greedy algorithm of always taking always first doing the things that will reduce the shape the most, then you will get the right answer. So you can use a greedy algorithm. In general, that doesn't actually, it's not guaranteed to give you an optimal result, but that'll work for these problems. And so here, the thing that will reduce the shape the most is doing the a times the x first. So I'm going to create a table similar to how we had it before, z1, and then we'll record the shape and the runtime. So z1 will be the a times x. And so here's our shapes listed up here. What's going to be the resulting shape of this multiplication? Yeah, just a vector m, or m by 1. What's the runtime? O of mn. So think of the x here as a matrix, n by 1. And so m times n, same n, don't include it twice, and then times the 1 over here. So O of mn. Now we have an m by 1 thing. We can't multiply that m by 1 thing until we've done this inversion. So we have to do that inversion first. In order to do the inversion, we have to do this operation right here first. So we'll do the AA transpose, Z2 equals AA transpose. And what's the shape of that going to be? M. What's the runtime of that going to be? N squared n. Here we'll have m times n times an n times m, so that m is going to come up twice, the n only once. And then our next thing that we'll do is take the inverse of the AA transpose. So Z3 equals Z2 inverse, like that. What's the shape of inverting a square matrix? Yeah, it stays the same, m by m. What's the runtime? Yep, cubic runtime. So anytime you think of inverting, multiplication, computing all of the eigenvalues, you should think cubic. And then finally, we have this inversion over here, this vector right here. We can multiply them together. Say Z4 equals Z1 times Z3. What's the shape of that going to be? Well, I apologize, I wrote that in the wrong order. Z3 should be on the left and Z1 on the right, just because that's how it's defined to be up here in the problem. And yeah, so Z3 m by m, Z1 m by 1. So it'll just be another m by 1 or m. And what's the runtime of that going to be? Of m squared. And so now we got a lot of different terms that we're going to be adding up together over here. I'll go ahead and just simplify in my head that the mn gets absorbed into the m squared n. This is guaranteed to be bigger than that, so we don't need this term right here. The m cubed is guaranteed to absorb the m squared, so we don't need this term right here. The n, anytime you have two terms that don't have the same variables, you'll have to include both of them. So of m squared n plus m cubed, like that. Any questions about how to do those sorts of problems? Okay, yeah, that'll become second nature by the end of the class. We'll be doing this for a lot of different algorithms. Yeah, that's it for today. If anybody has questions about anything else, I'll stick around as long as people want after class here. And I will hope you have a good long weekend. I'll see you all next week. Yeah.
I wasn't here last lesson in person, so welcome to
I have them in my office. You can walk with me.